Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. High above us, our sun is never truly calm. Its surface roils with nuclear fusion, magnetic fields twist and snap, and occasionally it unleashes a tempest of charged particles that race across 93 million miles of space toward Earth, at speeds exceeding 4 million miles per hour. These are solar storms, cosmic tsunamis of plasma and electromagnetic radiation that have shaped our planet's history and may yet transform our technological future. When a solar storm strikes Earth's magnetic field, the results can be both destructive and breathtakingly beautiful. The dancing aurora borealis, those ethereal curtains of light that paint the polar skies in greens and purples, are the visible signature of these storms. But beneath this beauty lies potential devastation. In 1989, a solar storm collapsed Quebec's power grid, plunging 6 million people into darkness for 9 hours. The economic impact exceeded $2 billion. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free and it helps us grow this community together. Solar storms begin with complex processes occurring in the sun's atmosphere. The photosphere, what we perceive as the sun's surface, maintains a temperature of approximately 5,500 degrees Celsius. Above it extends the corona, paradoxically heating to over 1 million degrees Celsius through mechanisms scientists are still working to fully understand. Within this superheated plasma environment, magnetic field lines become entangled like cosmic rubber bands. When these fields suddenly reconnect and release energy, an event called magnetic reconnection, a solar flare erupts. The most powerful solar events, coronal mass ejections, CMEs, blast billions of tons of solar plasma into space. These vast clouds carry their own magnetic fields and can cause geomagnetic storms when they collide with Earth's magnetosphere. The largest recorded solar storm, the Carrington event of 1859, produced aurora visible as far south as Cuba and caused telegraph systems worldwide to fail, with some operators reporting sparks flying from their equipment. Modern space-based observatories like the Solar Dynamics Observatory, SDO, and Solar and Heliospheric Observatory, SOHO, now monitor the sun continuously, providing early warning of potential storms. Scientists classify solar flares on a logarithmic scale from A, weakest, through C and M to X, strongest, with each letter representing a 10-fold increase in energy output. An X-class flare releases energy equivalent to millions of 100-megaton hydrogen bombs exploding simultaneously. For centuries, humans have viewed solar storms as threats, cosmic forces to be endured or, at best, predicted. But a radical shift in thinking is emerging among researchers across disciplines from astrophysics to electrical engineering. What if these powerful cosmic events aren't merely hazards to be mitigated, but vast untapped energy resources waiting to be harnessed? The concept sounds like science fiction, yet the underlying principles are rooted in established physics. Each major solar storm delivers energy to Earth's environment, equivalent to thousands of times our current global energy consumption. If even a fraction of this could be safely captured and utilized, it would revolutionize human energy systems overnight. To understand how we might harness solar storms, we must first comprehend their complex physics. The sun's outer layer, the corona, is not uniform but filled with regions of varying density and temperature. Where these regions meet, boundaries form, creating conditions for explosive energy release when the sun's magnetic field lines reconfigure. This magnetic reconfiguration process occurs through magnetic reconnection, a phenomenon where, oppositely, directed magnetic field lines break and reconnect in lower energy configurations. The excess energy converts into heat, light, and kinetic energy, accelerating charged particles to significant fractions of the speed of light. These particles, primarily electrons and protons, form the basis of solar radiation storms. Coronal mass ejections operate on an even grander scale. During a CME, magnetic fields on the sun's surface become increasingly complex until they reach a breaking point. The sudden reconfiguration releases not just energy, but massive quantities of matter, up to 10 billion tons of solar plasma, into space at speeds reaching 3,000 kilometers per second. When directed toward Earth, these solar emissions interact with our planet's magnetic field, a protective bubble called the magnetosphere that extends approximately 64,000 kilometers into space on the day side and stretches into a long tail exceeding 300,000 kilometers on the night side. This interaction compresses the magnetosphere on the sunward side and elongates it on the opposite side, creating a complex system of electric currents that flow throughout near-Earth space. Scientists observe these interactions using networks of ground-based magnetometers that measure changes in Earth's magnetic field and satellites positioned at strategic points in space. The Advanced Composition Explorer, ACE satellite at the L1 Lagrange point, a location 900,000 miles sunward of Earth where gravitational forces balance, provides crucial early warning of approaching solar storms. The strength of geomagnetic storms is measured using the K-index, a quasi-logarithmic scale ranging from 0 to 9. When a particularly strong storm strikes, it produces geomagnetically induced currents, GICs, that can flow through any electrically conductive infrastructure, including power grids, pipelines, and railway systems. The Sun follows an approximately 11-year cycle of activity, with the number of sunspots, relatively cool magnetically complex regions on the solar surface, rising and falling predictably. Solar Cycle 25 began in December 2019 and is predicted to reach its maximum around 2025. Each cycle varies in intensity. Solar Cycle 19, 1954 to 1964, produced some of the most powerful solar storms in recorded history. The scientific understanding of solar storms has advanced tremendously since the first telescopic observations of sunspots by Galileo Galilei in 1610. Space-based observatories now monitor the Sun across multiple wavelengths, revealing structures and processes invisible from Earth's surface. The Daniel K. Inouye Solar Telescope on Maui, Hawaii, the world's largest solar telescope with a 4-meter primary mirror, captures images of the Sun's surface with unprecedented detail, showing features as small as 20 kilometers across. Recent missions like NASA's Parker Solar Probe venture closer to the Sun than any previous human-made object, flying through the corona to measure the solar wind at its source. In 2021, the probe detected the specific magnetic field conditions necessary for magnetic reconnection, providing crucial data for understanding how solar storms begin. This growing scientific understanding reveals not just the destructive potential of solar storms, but also their immense energy content. Virtually all technologies for capturing solar storm energy depend on electromagnetic induction, the same principle that allows solar storms to damage power grids by inducing unexpected currents. Throughout history, solar storms have periodically wreaked havoc on human technology, with each event serving as a stark reminder of our vulnerability to cosmic weather. The Carrington event of 1859 stands as the benchmark for extreme solar storms. On September 1, 1859, British astronomer Richard Carrington observed an intense white light flare on the Sun. Within 17 hours, a massive coronal mass ejection struck Earth, producing aurora visible to the equator and inducing currents so powerful that telegraph operators could disconnect their batteries and operate solely on celestial power. More recently, in March 1989, a severe geomagnetic storm collapsed Quebec's entire power grid in 90 seconds. The province plunged into darkness as transformers overheated and protective systems failed. The same storm damaged a transformer at a nuclear plant in New Jersey and caused computer problems at hundreds of institutions across North America. In October 2003, the Halloween storms, a series of 17 major solar flares, over 3 weeks, forced the rerouting of aircraft, knocked out satellites, and triggered power outages in Sweden. Astronauts aboard the International Space Station, ISS, had to seek shelter in the most heavily shielded portions of the station as radiation levels spiked to dangerous levels. Today, our technological infrastructure is far more extensive and interconnected than during previous major solar events, creating unprecedented vulnerabilities. Modern power grids with high-voltage transmission lines spanning hundreds of kilometers make ideal antennas for geomagnetically induced currents. The longest lines can generate electrical potentials exceeding 1,000 volts during severe storms. The semiconductor-based electronics that control nearly every aspect of modern infrastructure are particularly vulnerable to solar events. While hardened military and aerospace systems incorporate radiation shielding, commercial electronics typically lack such protection. A sufficiently powerful solar storm could disable or permanently damage billions of electronic devices simultaneously. Global positioning systems and communication satellites operate directly in the path of solar radiation. During the October 2003 storms, approximately 80% of satellite-based communications experienced disruptions. Modern society's dependence on these systems for everything from financial transactions to agricultural timing creates cascading vulnerabilities across economic sectors. The economic implications of a Carrington-class event today would be staggering. A 2008 report by the National Academy of Sciences estimated that an extreme geomagnetic storm could cause $1 to $2 trillion in damage during the first year alone, with recovery taking 4 to 10 years. This exceeds the combined cost of the most destructive hurricanes in U.S. history. Current protection systems focus primarily on detection and mitigation rather than utilization. The Space Weather Prediction Center, SWPC, operated by the National Oceanic and Atmospheric Administration, NOAA, provides forecasts and warnings for significant solar events. Power grid operators can reduce load or disconnect vulnerable components when warnings are issued. But these measures sacrifice operational capacity to preserve infrastructure. Physical protective measures include series capacitors that block geomagnetically induced currents in power transmission lines and neutral ground resistors that limit current flow through transformer neutrals. However, retrofitting the entire North American power grid with such protections would cost an estimated $10 billion, a substantial investment that utilities have been reluctant to make for events that occur infrequently. The limitations of current approaches present both challenge and opportunity. Rather than merely defending against solar storms, a reactive posture that requires constant vigilance and accepts periodic damage, what if we could develop systems that actively benefit from these events? The conceptual shift from viewing solar storms as threats to seeing them as opportunities represents a fundamental change in our relationship with cosmic phenomena. This perspective draws inspiration from other fields where potentially destructive natural forces have been harnessed for human benefit: hydroelectric dams taming floods while generating electricity, or windmills transforming destructive gales into usable power. The theoretical framework for solar storm energy capture centers on electromagnetic induction, the same process that makes these storms threatening to power grids. When a solar storm strikes Earth's magnetosphere, it creates rapidly fluctuating magnetic fields. According to Faraday's law of induction, such changes induce electrical currents in conductive materials. Rather than allowing these currents to flow chaotically through infrastructure, dedicated systems could channel this energy into controlled, useful forms. Early research in this field began quietly in the 1970s following the oil crisis, when scientists at several national laboratories explored alternative energy sources. Declassified documents reveal that researchers constructed experimental arrays in Alaska and northern Canada, regions frequently exposed to geomagnetic activity. These primitive systems used mile-long copper wire arrays to capture induced currents during aurora events, storing the energy in early battery technologies. The results were promising but limited by materials, science, and energy storage capabilities of the era. These early experiments consistently demonstrated that significant electrical potential, often exceeding 100 volts per kilometer of conductor, could be generated during even moderate geomagnetic storms. However, the unpredictable and intermittent nature of solar storms made practical implementation challenging. Unlike solar panels that generate electricity during daylight hours or wind turbines that operate when breezes blow, solar storm energy arrives in unpredictable bursts, separated by days, months, or years of inactivity. This intermittency presents a fundamental challenge to integration with conventional power systems, which require consistent, predictable power generation. Modern energy storage technologies may finally bridge this gap. Advanced battery systems, pumped hydro storage, hydrogen production, and emerging technologies like carbon-neutral synthetic fuel production could all serve as mechanisms to store captured solar storm energy until needed. These technologies transform intermittent power sources into dispatchable energy resources that can be released on demand. Compared to conventional renewable energy sources, solar storm energy offers unique advantages. While a square meter of photovoltaic panel might generate 100 to 200 watts in full sunlight, the same area properly configured to capture geomagnetically induced currents could theoretically generate kilowatts or even megawatts during intense solar events, a 1,000-fold increase in power density, albeit for limited durations. Moreover, solar storm energy collection systems potentially require less physical infrastructure than conventional renewables. Rather than covering vast areas with solar panels or wind turbines, strategically placed conductive arrays in key geomagnetic hotspots could capture energy during solar events. These systems would have minimal environmental footprint compared to large-scale renewable projects. The field has attracted renewed interest as climate change drives exploration of all possible clean energy sources. Research institutions in Norway, Canada, and Russia, countries with territories extending into aurora zones, have initiated projects examining modern implementations of solar storm energy capture. These efforts combine historical research with contemporary materials science and advanced computer modeling of geomagnetic fields. Private companies have also entered this space. In 2022, startup Aurora Energy Systems secured $20 million in venture funding to develop geomagnetic harvesters, specialized energy capture systems designed to operate during solar storms. Their prototype installation, near Tromsø, Norway, has demonstrated promising results during moderate geomagnetic events. The cutting edge of solar storm energy harvesting lies in magnetohydrodynamic (MHD) energy conversion systems. Unlike conventional generators that use moving mechanical parts, MHD generators extract electricity directly from moving conductive fluids or plasmas. When solar storms create ionized particles in Earth's upper atmosphere, specially designed MHD channels can extract energy from these particles with no moving parts, achieving theoretical efficiencies exceeding 80%. Advanced MHD systems utilize superconducting magnets cooled by liquid helium to create powerful magnetic fields that maximize energy extraction from even relatively weak geomagnetic disturbances. Laboratories in Japan and Finland have demonstrated small-scale MHD generators that produce kilowatt-level power outputs during moderate aurora activity, with outputs scaling proportionally during stronger events. Complementing these technologies, ionospheric energy harvesting techniques target the electrically charged region of Earth's upper atmosphere, between 60 and 1,000 kilometers altitude, where solar storms create powerful electrical currents known as electrojets. These naturally occurring currents can carry millions of amperes during strong geomagnetic storms. Researchers have developed theoretical frameworks for tapping these currents using tethered balloon systems that extend conductive cables into the ionosphere. In 2023, the European Space Agency, ESA, launched the Atmospheric Coupling and Energy Transfer Explorer, ACTE, to map ionospheric currents with unprecedented precision. This mission is providing crucial data for optimizing ground-based collection systems by identifying electrojet hotspots where energy density reaches maximum levels. Perhaps the most ambitious approach involves orbital collection systems positioned at strategic locations in Earth's magnetosphere. The boundary regions where solar wind particles interact with Earth's magnetic field contain enormous energy potential. Engineers at the Massachusetts Institute of Technology, MIT, have designed conceptual magnetospheric energy collectors, spacecraft, with kilometer-long conductive tethers that would generate electricity as they pass through regions of changing magnetic flux. A prototype technology demonstration, the Magneto-Electric Power Satellite MEPS-1, is scheduled for launch in 2026. This small experimental satellite will deploy a 300-meter electrodynamic tether to test energy collection efficiency during various solar wind conditions, potentially opening the door to larger-scale systems. On Earth's surface, ground-based collection arrays represent the most immediately practical implementation. Modern designs bear little resemblance to early experimental setups. Today's systems employ graphene-enhanced conductors with resistance approaching theoretical minimums, allowing efficient energy capture across vast distances. Computer-controlled switching systems can reconfigure these arrays in real time to optimize collection based on the specific characteristics of each solar event. The northern territories of Canada and Russia have become focal points for these installations due to their proximity to the auroral oval, the ring-shaped region around Earth's magnetic poles where aurora activity concentrates. A major installation near Yellowknife, Northwest Territories, featuring 100 kilometers of specialized conductor arrays, demonstrated average power production of 8 megawatts during a moderate geomagnetic storm in January 2024. Materials. Science breakthroughs continue to enhance collection efficiency. Multi-layered metamaterials, engineered structures with properties not found in nature, can amplify weak geomagnetic fluctuations. Quantum sensors utilizing nitrogen vacancy centers in diamond detect subtle magnetic field changes with sensitivities approaching the theoretical quantum limit, allowing systems to begin energy collection hours before conventional detectors register storm activity. Energy storage remains crucial for practical implementation. Beyond conventional batteries, researchers are exploring Earth-abundant materials for thermal energy storage. These systems convert captured electrical energy to heat stored in molten silicon, salt, or specialized phase change materials at temperatures exceeding 1,000 degrees Celsius. This stored thermal energy drives conventional turbines to produce electricity on demand. The integration of artificial intelligence optimizes these complex systems. Machine learning algorithms analyze data from satellites and ground-based sensors to predict optimal collection configurations minutes to hours before peak storm conditions arrive. During the March 2024 geomagnetic storm, AI-managed systems demonstrated 35% higher energy capture compared to manually configured arrays. The unique characteristics of solar storm energy, intermittent but extremely high-density power delivery, suggest specialized applications rather than direct integration with conventional baseload power generation. Perhaps the most promising application lies in hydrogen production through electrolysis. When solar storm energy becomes available, electrolyzers can convert water into hydrogen gas, effectively storing the electrical energy in chemical form. This hydrogen can later fuel everything from vehicles to industrial processes without carbon emissions. Several pilot projects are exploring this approach. In northern Sweden, the Aurora Hydrogen Initiative uses geomagnetic energy to produce green hydrogen when solar storms occur. The project has demonstrated production costs potentially competitive with conventional hydrogen sources, particularly as carbon taxes increase globally. For grid integration, advanced power electronics serve as crucial intermediaries. Solid-state transformers utilizing silicon carbide and gallium nitride semiconductors can handle the rapid fluctuations characteristic of solar storm energy, conditioning this power for safe grid connection. These systems incorporate sophisticated surge protection and isolation mechanisms to prevent damage from unexpected energy spikes. One of the most compelling applications for solar storm energy lies in remote and disaster-resilient power systems. Arctic communities and research stations experience frequent aurora activity, but traditionally rely on diesel generators for electricity. Prototype solar storm harvesting systems installed at the Kakslautanen Arctic Resort in Finnish Lapland now provide supplementary power during geomagnetic events, reducing diesel consumption by an estimated 22% annually. Disaster resilience represents another key application. After major natural disasters, conventional power infrastructure often fails precisely when energy is most needed. Solar storm harvesting systems could provide emergency power independent of damaged grid infrastructure, particularly valuable for critical facilities like hospitals and emergency response centers. Beyond Earth's surface, space-based applications present fascinating possibilities. The International Space Station, ISS, and future space habitats exist directly in the environment affected by solar storms. Rather than merely shielding against these events, next-generation space stations could incorporate collection systems that convert harmful radiation into usable energy, essentially turning a safety hazard into a resource. Looking further ahead, interplanetary implications emerge. Mars lacks a strong magnetosphere, exposing its surface to solar radiation. Future Martian settlements could deploy artificial magnetospheres, essentially massive electromagnets that both shield colonists and generate power from the very radiation they deflect. Similar principles apply to habitats throughout the solar system, from Mercury to the moons of Jupiter. The timeline for widespread technology development spans decades rather than years. Laboratory-scale demonstration systems are operational today, with commercial pilot projects beginning operation in the 2020s. Full-scale commercial deployment will likely occur in the 2030s, coinciding with solar cycle 26, which astronomers predict may bring increased solar activity. Technical challenges remain. Energy capture systems must withstand extreme electromagnetic conditions that can damage conventional electronics. Materials must maintain performance through temperature fluctuations and radiation exposure exceeding normal design parameters. Storage systems must scale economically to handle the massive energy impulses characteristic of major solar events. The long-term vision extends beyond merely capturing energy from Earth's magnetosphere. Some researchers propose artificial magnetospheric enhancement, essentially strengthening Earth's natural magnetic field in specific regions to increase energy collection capacity. While controversial and technically challenging, such approaches might eventually allow humanity to modify space weather effects rather than simply responding to them. The transition from theoretical concept to practical implementation has accelerated dramatically in recent years. What began as speculative research has evolved into functioning prototypes with demonstrable energy production, with each solar maximum bringing increased opportunities for system testing and refinement. Solar storm energy harvesting moves steadily from scientific curiosity toward practical energy resource. As with any transformative technology, the emergence of solar storm energy harvesting raises profound ethical questions about access, control, and distribution. The geographical reality that aurora phenomena concentrate around Earth's magnetic poles creates natural advantages for nations with territories in these regions. Canada, Russia, the Nordic countries, and to some extent the United States through Alaska, have natural access to the most energy-dense regions for collection. This geographical disparity could potentially create new forms of energy inequality unless intentionally addressed through international frameworks. The United Nations Office for Outer Space Affairs, UNOOSA, has proposed a common electromagnetic heritage doctrine that would classify solar storm energy as a resource belonging to all humanity, similar to existing frameworks for deep seabed, minerals or radio frequency spectrum. Geopolitical considerations extend beyond resource access to infrastructure security. Large-scale energy collection arrays could become critical infrastructure vulnerable to sabotage or military action. Their remote locations in sparsely populated regions complicate physical security, while their electromagnetic nature creates unique cybersecurity challenges. The dual-use potential, systems designed for energy collection, could potentially be repurposed for communication disruption or other electromagnetic operations, further complicates international governance. Environmental impacts, while generally favorable compared to fossil fuels, still require careful assessment. Large conductor arrays create electromagnetic fields that may affect migratory animals that navigate using Earth's natural magnetic field. Preliminary studies on bird and marine mammal migration patterns near experimental installations show minimal disruption, but long-term effects remain unknown. The physical footprint of ground installations is relatively small compared to conventional renewable energy, potentially reducing habitat disruption and land use conflicts. Preparing society for a new energy paradigm requires both technical preparation and cultural adaptation. Energy systems designed around predictable, controllable generation must evolve to accommodate the inherent variability of solar storm energy. Smart grid technologies capable of rapidly adjusting to sudden energy influxes become essential infrastructure components. Energy storage systems, from batteries to pumped hydro to hydrogen production, must scale dramatically to buffer the intermittent nature of this resource. The cultural dimension involves shifting public perception of solar storms from threat to opportunity. Educational initiatives like the Solar Stormwatch Citizen Science Project engage the public in monitoring space weather while explaining potential benefits. Several northern communities have initiated energy festivals, coinciding with major aurora events, celebrating both the visual spectacle and the clean energy being harvested. Looking forward, the next steps in research and development focus on three parallel tracks. First, improving prediction capabilities to maximize energy capture from each solar event. The Digital Magnetosphere Project, a massive computational simulation incorporating data from dozens of satellites and thousands of ground stations, aims to predict geomagnetic conditions with 6-hour accuracy by 2027. Second, materials science research continues to develop more efficient conductors and energy conversion systems. Quantum metamaterials that enhance natural electromagnetic induction could potentially double or triple energy capture efficiency. Advanced manufacturing techniques are reducing costs of specialized components, making widespread deployment economically viable. Third, storage and distribution systems continue to evolve. Beyond conventional batteries, promising approaches include gravitational potential energy storage, using excess electricity to lift massive weights that generate power when lowered, and advanced thermal storage using novel phase change materials. As humanity faces the twin challenges of increasing energy demand and climate change, every potential clean energy source deserves exploration. Solar storm energy represents not just a novel approach to power generation, but a philosophical shift in our relationship with cosmic phenomena. Rather than merely protecting ourselves from space weather, we may soon find ourselves eager for the next solar storm, watching auroral displays with appreciation not just for their beauty, but for the clean energy they deliver. The story of solar storm energy harvesting reminds us that apparent threats often contain hidden opportunities. With scientific ingenuity and thoughtful implementation, tomorrow's technology may transform one of nature's most powerful and unpredictable forces into a resource for human advancement and environmental stewardship.